All right, good afternoon, everyone. My name is Lukas Rauter, and I'm with Silicon Austria Labs, working for the Sensor Systems Research Division. And today, I would like to present you something on the comparison of printed silver heaters and LIG fabricated heaters and their reliability before and after Parylene-C coating, and of course on their heating performance. So first of all, let's ask the question, why printed? Why LIG heaters? Why flexible heaters? There are some advantages. I would like to focus on a few of them. Of course, we have a flexibility, a very strong flexibility on the design of those elements. What does not only mean we are able to print different shapes or to print different geometries, but also we are able to print or to fabricate via LIG onto different shapes, onto three-dimensional shapes. They are thin and lightweight, therefore they are very easy integratable or can be embedded in other materials, or also, in systems, like you can combine them easily with other components and can customize them and adapt them therefore for smart systems. As we know from printed electronics, of course, their production is fast and very cost effective. They are energy efficient since there is a more direct heat transfer than compared to conventional elements, and we have a large variety of materials. What does not only mean the materials which we can use for their production, but also the materials where we can put them on, where we can fabricate them on, the substrate materials in this case. So what are the potential applications for printed and LIG heaters? There are already a few industries which study their potential applications, for example, wearables and smart textiles. It's possible to monitor with temperature sensors and then to regulate the body temperature with smart clothing devices or smart clothing. We have medical applications and diagnostics where heating pads or heaters, heat plasters are used for pain relief and for the temperature regulation in portable medical devices. The automotive industry is actually testing printed heaters for being embedded in car seats or steering wheels for the heating of those parts, but also for integration in exterior parts of cars, for example, the exterior mirrors and de-icing them in winter. As we heard on Monday, they are used in the advanced energy industry for efficient heating of buildings and houses, and in electronic devices for the dehumidification and temperature control. Good, so let's take a look at what we have done actually. We fabricated one printed heater. Of course, we fabricated more samples, but one sample was printed with the outer dimensions of 76 times or by 12.4 millimeters square, and an LIG heater with the same outer dimensions in order to somehow meet or somehow achieve similar resistance values. The screen printed heater and the LIG heater were both fabricated on 75 micrometer thick PI substrate. The printed one with a silver nanoparticle ink and the LIG one with a CO2 laser and 1000 ppi image raster density at the power of 3 watts. Further, a Parylene-C coating was attached. Why Parylene-C coating? Well, Parylene-C is known to be something like the gold standard material for coating in electronics industry, and this now for several years. So we put the Parylene-C coating on top of 5 microns thickness with a deposition rate of 3 microns per hour. So let's come to the characterization of the heaters. The screen printed heater consists of 8 meander loops with 500 microns width and also 500 microns spacing in between, while the LIG heater only consists of 1 loop. Like I said before, this is because we wanted to achieve similar resistance measurements to be able to compare them. Then we applied a voltage from 5 DC voltage from 5 to 15 volts with 2.5 volt increments and measured the heaters or monitored them with a thermographic camera. On the top pictures, you can see the thermography images of, on the left side, the printed heater, on the right side, the LIG heater. And as you can see on the plot, both heaters show similar heating behavior with a quadratic dependency of the heating power on the applied voltage according to Joule's law. And the only main difference here, I would say, is that we have seen bigger differences or deviations of the average value of the temperature value in case of the LIG heater, what is probably due to a more inhomogeneous surface of the heater itself. So the same thing was then done after the Parylene-C coating. And as we can see here, the average temperatures decreased by 13.6% for the screen printed heater and 14.8% on average for the LIG heater. Why is this happening? Of course, if you put a coating on top of the heaters, what is happening? You add thermal mass, and this also needs to be heated up. And second main factor here is the Parylene-C coating works something as a shielding for the thermal radiation. So in the next step, we put both heaters under accelerated live testing at 93% relative humidity and 40 degrees Celsius in a climate chamber for 291 hours, which corresponds to 337 days, according to Arrhenius-Peck relationship for ALC. And what we have seen here is that the silver heaters, the coated ones and the uncoated ones, and also the LIG heater, but in this case only the coated one, stayed stable over the whole testing time, more or less stable. The uncoated LIG heater started already to degrade after not even 1 day, and its resistance increased by 74% on average. You can see here that the uncoated silver heater even decreased its resistance. This might not understandable, but if you think about what happened, this is a post-curing effect. What happens? Some residues of the solvents still evaporate. This can only happen in case of the uncoated heater. In case of the coated heater, it's like encapsulated and nothing can evaporate anymore, so resistance stays stable in this case. Good. Last but not least, we are always talking here of flexible heaters, so we also want to show that they are really flexible. And we went for bending tests and put them in a 2-axis flexible bending machine. Did 1000 repetitions with a bending radius of 24.2 millimeters, which bends the samples into a semicircle. After 400, or let's say up to 400 repetitions, all our samples kept stable. Above that, the silver samples kept stable, but the LIG samples started to degrade. The coated one less than the uncoated one. This happened. We checked that under the digital microscope. In addition, and that was because the LIG starts to ablate and starts to peel off after several repetitions in bending from the substrate, and therefore you lose conductivity. So let's sum this up. We have seen a comparison of printed silver heaters and LIG heaters, their heating performance, coated and uncoated, with Parylene-C. Silver was or has shown to be more stable compared to LIG, at least for accelerated life testing. The LIG heaters need to be coated. And yeah, for the future work, we want to go with multi-physics simulations to get a more uniform, a more homogeneous distribution of temperature and heating over this area of 76 by 12.4 millimeters square, which we have chosen because of our application. And yeah, then we want to integrate those heaters in smart systems compared with sensors. Thank you very much.